Fusion of hydrogen or helium normally requires at least the conditions found in the cores of stars. High temperatures and densities allow hydrogen and helium nuclei to get close enough to fuse together into bigger nuclei and release a ton of energy, powering even more fusion while releasing enough extra to power the star. Or if you set this situation up on Earth, you might have a hydrogen bomb. But it's actually possible for fusion to occur at temperatures much, much lower than the core of the sun. Like room temperature, for example. Now, I'm not talking about the infamous cold fusion of the 1980s that hasn't been shown to work or involve any, well, fusion. No, I'm talking about the room temperature fusion of the 1950s that actually does work. Fusion with the help of muons. Nuclear fusion, of course, happens when atomic nuclei, like hydrogen nuclei, come close enough together that their strong nuclear attraction can overcome their electric repulsion, and they fuse together into a single, bigger nucleus, like helium. This typically happens in a plasma, that is, a super hot soup of electrons and atomic nuclei, where if it's hot enough, every once in a while, two nuclei bump hard enough into each other to fuse. But fusion can, in principle, happen in regular, non-plasma molecules too, like the hydrogen molecule, in which two hydrogen nuclei are kept relatively near to each other by sharing electrons. The nuclei don't stay separated a rigid distance apart, though. They vibrate and wiggle, and every so often they can, in principle, get close enough to fuse together. But with hydrogen, or nitrogen, or oxygen, or pretty much all other molecules, this happens exceedingly rarely, which is why our atmosphere, which has a fair amount of molecules, isn't a giant fusion bomb. However, things are different if you replace the electrons with particles called muons, which are basically exactly the same as electrons, except 200 times heavier. Muons, being essentially heavy electrons, form atoms and molecules in almost the exact same way as electrons, but since they're heavier, their orbits are much closer to the nucleus than an electron with the same energy and angular momentum would be. And this means that atoms and molecules held together with muons instead of electrons are about 200 times smaller, and their nuclei are correspondingly about 200 times closer together. And being closer together makes nuclei many, many, many times more likely to fuse together. So much so that the nuclei in hydrogen molecules made with muons can fuse together at temperatures much lower than the core of the sun, even room temperature, which was predicted in 1947 and experimentally achieved in 1956. Physicists have even managed to achieve muon-aided nuclear fusion at temperatures close to absolute zero. So at this point, you're probably asking yourself, if room temperature nuclear fusion exists, why aren't we using it to power modern civilization? Well, while muon-facilitated fusion is indeed fully legit nuclear fusion at non-crazy temperatures, there are some major problems which prevent it from being used as a power source. First, muons don't live very long. Unlike electrons, which have an, in principle, infinite lifespan, after about 2 microseconds, muons spontaneously decay into an electron and some neutrinos. So if you're going to do anything with muons, you have to do it real quick. This turns out not to matter much for the purposes of facilitating fusion, but because of their short lifespan, there aren't a ton of muons around. So if you want a reliable supply of muons, you pretty much have to make them with a high-energy particle accelerator, which takes a lot of energy per muon, at best about 5 giga-electron-volts, or about 50 times the E=mc² mass energy of a muon itself. Now, luckily, you don't need a muon for every single pair of hydrogen nuclei you want to fuse, because after a pair of nuclei fuses into helium, the muon can go off and help more nuclei fuse, and then help more. And more, and more. Except every so often, the muon doesn't. It'll get stuck as part of the newly fused helium atom, and can't facilitate any additional fusing. This means that each muon only helps an average of 150 fusions of nuclei before it gets stuck. And since each fusion of nuclei releases about 18 mega-electron-volts of energy, this means that after 150 fusions, each muon will have facilitated an average of 2700 mega-electron-volts, or 2.7 giga-electron-volts, of energy generation, which means that unfortunately the numbers don't add up. Remember, it currently takes around 5 giga-electron-volts of energy to produce a muon, but each muon only generates about 2.5 giga-electron-volts of energy before getting stuck to a nucleus. That is, muon-facilitated fusion is a net consumer of energy rather than being a source of energy. This is the best case possible with current technology, and the numbers are still off by a factor of 2 before even reaching any sort of break-even where muon muon-facilitated fusion could generate as much energy as it consumes. And we'd need to be much better than just breaking even, energy-wise, to make a viable commercial power plant. Pretty much the only hope for muon-facilitated fusion is to figure out how to make muons for less energy, or to figure out how to have less of them stick to the helium nuclei, or how to unstick them once they're stuck. Which are all hard problems limited by the unchangeable physical properties of muons and nuclei, and so we've made quite slow progress in over 70 years of research. The summary is that muon-induced fusion exists. It's fascinating science, but it's not going to be powering the world anytime soon. To dive deeper into the energy sources that do power the world, I highly recommend checking out the Fuel the World course on Brilliant.org, this video's sponsor. Fuel the World is part of their series on the physics of the everyday and guides you through the basics of solar power, fossil fuels, nuclear reactions, Dyson spheres, and how much energy mammals need to survive. There's even a section about the fusion reactions that happen in the sun. And the physics of the everyday course as a whole gives a great overview of the physics of household items, sports, weather and climate, and more. And the first 200 people to go to brilliant.org/minutephysics can get 20% off of a premium Brilliant subscription with access to all of Brilliant's courses and puzzles. Again, that's brilliant.org/minutephysics, which gets you 20% off premium access so you can seriously hone your math and science skills. And it lets Brilliant know you came from here.